Welcome to another edition of Math for No Reason. In this edition, we are looking at this problem. Here, the set B is a subset of A and f is a function whose domain is A and the codomain is B, and it is 1, 1. Then the claim is that there exists a function h whose domain is A and the codomain is B, which is a 1, 1 corresponding. Suppose B is a subset of A and B is not equal to A, and define f0 to be the identity function of A, and f kx, this is the kth iterate of fx, and that is defined as f of f k minus 1 x. Now define the set C as the union of n greater than equal to 0 fn of a minus b. Now we define h to be a function from a to b, and h of a is same as fa if a belongs to this set C, and is equal to a if a belongs to the set a minus c. We will show that this function h is a 1, 1 correspondence. Note that a minus b is a subset of C. Why? Because f0 a minus b is a minus b, because f0 is the identity function on A. So every point in a minus b is in C, so a minus b is a subset of C. Now for the second part, fc is a subset of C. If we take a point u in fc, then there must exist a point v in C such that u is equal to fv. That is by the definition of fc. Now, since v belongs to C, by the definition of C, there must exist an n0 which is greater than equal to 0 such that v belongs to f n0 a minus b. Now, if we apply f on this point v, then we see that u would belong to f n0 plus 1 a minus b, which means that u also belongs to C from the definition of C. So therefore, we have a minus b is a subset of C and fc is a subset of C. Now suppose that n is greater than m, greater than equal to 0. We claim that fm a minus b intersection fn a minus b is the null set. To do that, we use the method of contradiction. So suppose we have x and x dash both in a minus b such that fmx is equal to fn x dash. Now if this happens, then we would have an element in this set fm, but we note that fn x dash is fm into fn minus m x dash. So that is by the definition of fn. Now that would mean that f of n minus m x dash is equal to x. So f of n minus m x dash is equal to x, and we have started by taking x in a minus b, so this x is in a minus b. But we also note that f is a mapping from a to b, so all iterates of it are elements of b. So f of n minus m x dash also belongs to b, that is x belongs to b. But we know that there is no element in common with a minus b and b. So a minus b intersection b is a null set. But this element x we are seeing is both in a minus b as well as in b, which is not possible. So our assumption, there exists two such integers n and m for which fmx is equal to fnx dash is false. So there is no element in common between fm a minus b and fn a minus b. Now let us try to show that h is 1, 1. Now suppose ha1 is equal to ha2. Note that since f is 1, 1, if a1 a2 both belong to C, then a1 must be equal to a2. Also, if a1 a2 belongs to a minus c and on this it is just the identity function. So then also a1 is equal to a2. So the only possibility for this to happen is that a1 belongs to C and a2 belongs to a minus C. Now we have that f of a1 is equal to a2. So since a1 belongs to C, f a1 belongs to fc, and fc is a subset of C. So this element a2 belongs to C, and also by assumption a2 belongs to a minus C. Now that is impossible. An element cannot be in C as well as in a minus C. So therefore, there is no such element for which if a1 is equal to a2. Thus we can conclude that H is 1, 1. Having proved that H is 1, 1, we now proceed to show that H is onto. For that, we first note that H of A is Fc union A minus C. Fc is coming from here, all the points Fa where A belongs to C, and A minus C is coming from here where Ha is equal to A if A belongs to A minus. Now, H of A is equal to F of, and we are putting down the definition of C here, union of n greater than equal to 0, Fn A minus B, union A minus C, A minus, again this is the definition of C here. Now observe that all these sets here we have proved earlier are disjoint sets. So therefore, this would become union of n greater than equal to 1, Fn A minus B, union this whole thing, A minus union n greater than equal to 0, Fn A minus. Now if you look at this, you see that this contains all terms except the first one, that is for the term n is equal to 0, and we note that f0 we had defined as IDA, that is the identity function on A. So therefore f0 A minus B is A minus B. So what we have now is A minus B, and that is exactly the set B. So we have shown that H of A is equal to B, and that is H is onto. Hence, we can conclude that H is a 1-1 correspondence. This is a very important result which is used to prove the Schroeder Bernstein theorem, which we will do next. The Schroeder Bernstein theorem states that if there are 1-1 mappings F from A to B and G from B to A, then there is a 1-1 correspondence between the sets A and B. So we will use this above result to prove this very famous theorem. Let A naught be equal to GB, and since G is from B to A, so GB is a subset of A, and B naught B is equal to FA, which is a subset of B. Now if you can think of another function G naught which goes from B to A naught, and G naught B is equal to GB. That means it's the same function GB, but the codomain is now restricted to A naught. And similarly for F naught, the codomain of this function f is restricted to B naught. So these are two functions which are induced by these functions f and g, and we note that these are both 1-1 correspondences. G and f were both 1-1 mappings, and now since we have restricted the codomain to its range, we get that G naught and F naught are both 1-1 correspondences. Now let us consider K, which is F naught composed with G naught, and this is a function whose domain is B and the codomain is B naught. Since both F naught and G naught are 1-1, K is 1-1, and since B naught is a subset of B and K is 1-1, we can invoke this result and we can find the function H going from B to B naught, which is a 1-1 correspondence. Now, if we have a 1-1 correspondence, it has an inverse function here, H inverse, which we have called H dash, which goes from B0 to B and is also a 1-1 correspondence. Now, if we compose H dash with F0, then we have a function A to B0 and then B0 to B. So it's H dash composed F0 is a function from A to B, which is also a 1-1 correspondence, because the composition of two 1-1 correspondence is again a 1-1 correspondence. Thus, we have shown that there is a 1-1 correspondence between the two sets A and B, and we have proved the Schroeder Bernstein theorem. Thank you.